Number 9. Show that the sum of the vectors discussed in example 3.2 gives the result shown in figure 3.24. All right, so I copy and pasted example 3.2 here, and figure 3.24 is over on the right-hand side. But just pretend that we don't have the figure yet, and let's just see what we can do when we read through the example. All right, so it says that a woman sailing on a boat at night is following directions to the dock. The instructions read first to sail 27.5 meters in a direction 66 degrees north of east from her current location, and then travel 30 meters in a direction 112 degrees north of east, aka 22 degrees west of north. All right. Then it says if woman, if she makes a mistake or whatever, then that she goes the opposite direction, where will she end up? But the picture, they really want us to just take into account the information before she makes the mistake, meaning where's the dock? Okay. So let's outline the two vectors here. So the first vector is the 27.5 meters at 66 degrees north of east. So that's V1. So I'm going to write that as 27.5 meters at 66.0 degrees north of east. Then vector 2 is 30 meters at 112 degrees north of east. I'm going to use the shorthand 22 degrees west of north, okay? So V2 is 30.0 meters at 22.0 degrees, oh, that's not squared, 0 degrees west of north. All right, so let's look at these individually. What we're going to do is we're going to use the component method. All right, so basically in order to find the resultant, we have to sum the components of all of the individual vectors. So I'm going to set up my component table right now. So I'm going to do component table, A-B-L-E. Oh, let's underline that. So we have the X and the Y. And from here, we're going to have V1. I'm going to put its components in here. And then I'm going to do V2 and put its components in over here. All right. So first, let's look at vector number 1, or V1. So first, to find the components, simply draw a set of axes. Okay. And remember, this is for V1. So now it says that this vector is 66 degrees north of east. So what does that look like? Excuse me. So what does that look like? Well, it looks something like this, right? An arrow there, and has the tip. Here's the 66 degrees north of east. I'm not going to put in all the decimals. And the value of the vector is 27.5. Okay, so what are the components of this? Well, start at the origin, and let's go out on the x-axis. Oh, I drifted off there a little bit. So this would be the x component, and it's positive. And then the y component of that vector would now be straight up. Okay, so that's also positive. Great, so let's simply now calculate the x component. How do we do that? Well, we know the hypotenuse of the triangle, we know the angle, and this side is considered the adjacent side. Therefore, it sounds like a cosine function. So cosine of theta is equal to adjacent over hypotenuse. Cosine of 66 is equal to positive x over 27.5. So simply now x is equal to, just take out the calculator and do 26, where we got it, cosine of 66 times 27.5. And the answer comes out to, we'll do 3 sig figs, 11.2. 11.2 meters. So that's the x component's value. Okay, now let's look at the y component. So here you're solving for y. Again, we know the hypotenuse, we know the angle, and we're looking for the side opposite of the angle. Sounds like a sine function to me. So sine of theta is equal to opposite over hypotenuse. Sine of 66 is equal to y positive over 27.5. So now simply take that and plug it into the calculator. So sine of 66 times 27.5 works out to be 25.1. 25.1 meters. Now these are the components of V1. So let's put them into the table. So the x component of V1 was 11.2 meters and the y component was 25.1 meter. Wonderful. Now let's take a look at V2. All right, so what I'm going to do is I'm going to draw its axes now. Let's draw them over here. Okay, and we have, this is for V2. And V2, it says that it's 22 degrees west of north. So here's north, here's west, and then we got to be 22 degrees west of north. So that's probably going to be somewhere around here. Right? Let me make it a little straighter. Okay, one more time. And it's not going to work. So, okay. This angle in here is going to be 22 degrees. The length of the line is going to be 30. I'm going to leave out the decimal just for simplicity's sake. And now we have to consider what are the components. So it looks like we have a nice y component here, a nice positive y component here. So start at the origin and then go up. Okay, this would be the positive y component. And then we have an x component here to get to the tip of the resultant, and we had to travel in the negative x direction. Okay, so we have a positive y component and a negative x component here. And I just realized I drew this a little close to my table. So let me just move this down. Sorry about that, guys. Move it down to there, give myself some room. Okay, so now let's first calculate, doesn't matter which we do, let's calculate the y value first, okay? So remember y, in order to do that, we know the hypotenuse, we know the angle, and y is the adjacent side relative to the angle. So therefore, we're going to be using cosine. So cosine of theta is equal to adjacent over hypotenuse. Cosine of 22 is equal to the positive y value over 30. And now that means y would simply be cosine of 22 multiplied by 30. And that works out to be 27.8. So this is 27.8 meters. Great. Now let's do the same thing for the x component here. Here it is. So how do we solve it? We know the hypotenuse, we know the angle, and we're looking for the side opposite of the angle. Therefore, it's a sine function. So sine of theta is equal to opposite over hypotenuse. Sine of 22 is equal to negative x over 30. So now negative x is going to equal sine of 22 times 30. Okay, so it comes out to be 11.2 meters. And then the x value will now just move the negative sign over, negative 11.2 meters. And that's the x component. Let's plug those values in now to our component table. So the x component of v2, right, of vector 2 was now 11, negative 11.2 meters. Interesting. And the y component was now 27.8 meters. Wonderful. Now, remember the overall rule here. To find the resultant vector, okay, let me just bring this divider down a little bit. To find the resultant vector, all we need to do is simply add these two together, v1 and v2, the components of each. So let's add these components together. When we add that, what do we get? 0. And now let's add these together. And what do we get? Looks like it's going to be about 52.9, I think, meters. Okay, great. Now, these are the components of my resultant vector. So if I had to draw a picture, right, if I had to draw it now in a coordinate system, how would I do it? So take a look. Here we go. Here's the coordinate system, the y-axis and the x-axis. Let's first start with the x-coordinate. So when we look back, what is the x component of my resultant vector? Big old Zippo, so 0. So it has no x component. Okay, what's the y component? Positive 52.9 meters. So we start at the origin, and we're going to draw a line straight up, and the magnitude of that is going to be 52.9 meters. So 52.9 meters. Okay, and what direction is it? It's due north, straight north. So this thing right here, this red line represents the resultant vector. Now, take a look at the picture on the upper right-hand corner. Guess where the resultant vector is? It's right here. There's the resultant in red. And what's its value? Oh, look at that. Right on the money. 52.9 meters. Now this picture, in my opinion, this picture is a good picture, all right, because it shows you when you look at when you do the tip to tail method, right, and you put the first vector A, you write that, and then starting at the tip of A, you put the tail of B, and you write its directional component, you get a good feel for what the resultant should look like. Now, that's great, but you don't even need that in terms of being able to find the resultant vector's components. You can do it all analytically like I did. You look at each vector individually in terms of their pictures, get their components, make sure you're putting, if it's a negative x component, you got to make sure you put the negative value. If it's negative y, it's negative, right, etc. Plug it into your component table, add them up, and voila. You got your coordinates and you got your components of the resultant vector. So that takes care of that. Thank you guys for tuning in. Hope this helped. Please remember to subscribe. It definitely helps us. Thank you so much. Until next time.